right now. Sharing my screen. Okay, so can you see my screen now? Yes, cool. Okay, so we're very, very glad to have here the opportunity to listen to Nora Loose, who will present her work. So just to give a bit of background here. So with the scientific organizing committee, we decided to try and find keynote speakers that would have published innovative pieces of work over 2021, covering mostly those three topics that we were thinking could be interesting for the workshop. So as a reminder, this question of how we may use ocean models for preparing or better exploiting ocean observing networks, how we can use ocean models for better understanding the variability and the processes, and also questions related to the formulation, the design, and the sensitivity of ocean models to their input parameters. So this basically covers the sort of three keynote presentations that we'll have over the next 3 days. And the first one will be given by Nora. So you have here some of her background information. I imagine many of you already know her or have read the papers she published over the last couple of years. In particular, you have here all the contact information. We're very, very glad to have to give the floor to Nora here. This is a bit of a new format for the DRAKKAR workshop, to have like a keynote presentation. It's really because it's also coming with the virtual format, but I think that's a very good opportunity to get like more in depth into some presentations. So I'm very, very glad to give you the floor, Nora, for this first keynote presentation of the 20th DRAKKAR Ocean Modeling Workshop. So you'll have something like about 25 to 30 minutes for presenting your work, and then we'll have 15 minutes for questions and answers. And please, that's your turn.
Okay, can you see my screen? Yes. Well, thank you so much, Julia, for this nice introduction and for inviting me to give this keynote talk at the DRAKKAR workshop. This is a great honor for me. I'd like to talk about how adjoint models and uncertainty quantification can be leveraged to design ocean climate observing systems. And this is work that I did during my PhD and my first postdoc year at UT Austin with Patrick Heimbach. So ocean observing systems are absolutely crucial for understanding the ocean's role in climate and for evaluating climate model simulations. But they are pretty difficult and expensive to build and maintain. So the OSNAP array is a great example. It was recently deployed in the subpolar North Atlantic, and the OSNAP array has led to, I'd say, revolutionary new insights into North Atlantic Ocean circulation over the last 3 years or so. But to put all these instruments in the water and to maintain them over the years is a huge and costly effort. I believe it costs $30 million to keep this observing system up and running for 5 years. And this is just the funding that comes from the US side. So in this talk, I want to talk about one way in which ocean models can inform the design of effective observing systems. And the idea is simple. We want to use oceanic teleconnections that propagate observational constraints over long distances. So getting back to our OSNAP array, shown by this green line here, the primary goal of the OSNAP array is to monitor overturning and local transports across the section, the OSNAP section. But the ocean is connected, right? For example, via these surface currents that I'm showing in this map here. So it's reasonable to expect that the OSNAP array does not only carry information about what's happening at the array itself, but also in regions away from the array. So in the first part of my talk, I'll discuss oceanic teleconnections in the North Atlantic and how they can be uncovered systematically with an adjoint model. And in the second part, I will show that uncertainty quantification and ocean state estimation is a useful framework that formalizes some of these concepts from part 1. And part 1 and 2 together give us then a framework that can inform the design of effective ocean observing systems. I think, Julia, you're not muted, so maybe you could do this because we hear some background noise. Thank you. So let's first look at some oceanic teleconnections in the North Atlantic. To illustrate some teleconnections we don't usually think about, I will show 2 perturbation experiments with the MIT GCM. In the first experiment, I will perturb wind west of Iceland in this first green box. In the second experiment, I will perturb wind west of Africa in the second green box. And in both experiments, we will investigate how North Atlantic circulation and temperature react to these wind perturbations. And we will in particular be interested in how these perturbations impact 2 things. First, subsurface temperature at one OSNAP mooring here in the Irminger Sea. And second, heat transport across the Iceland-Scotland Ridge, which I'm showing by this yellow line. So before looking at these experiments, I will just mention that I'm using the MIT GCM in its global Echo version 4 configuration, which is relatively coarse, 1 degree it has 1 degree horizontal resolution. But since we are interested in these large scale teleconnections, we consider this setup good enough for now. So in this first experiment, I will perturb wind west of Iceland in this green box. And the red and blue arrows show warm and cold ocean currents respectively. So let's see what happens. So if we increase the northward wind in this green box, the ocean flows east, we get Ekman onshore convergence and a positive pressure anomaly along the Icelandic coastline. And the anomalous pressure gradient spins up an anomalous clockwise barotropic circulation around Iceland. And this anomalous circulation pattern will then weaken the Norwegian Atlantic current. And it will also weaken the East Greenland current. So how does this flow affect temperature at 300 meters depth? Well, as predicted by the mechanisms that I've just shown you, there's a cold temperature anomaly propagating into the Norwegian Sea due to a weakened warm Norwegian Atlantic current. And at the same time, there's a warm temperature anomaly propagating into the Irminger Sea due to a weakened cold East Greenland current. So to summarize, wind west of Iceland drives an anti-covariation between Iceland-Scotland Ridge heat transport and Irminger Sea subsurface temperature through a shared adjustment mechanism. And we'll get back to this later. But let's first look at the second experiment. So in this experiment, we will perturb wind west of Africa. And it is useful to first look at the response in bottom pressure. So if we increase the northward wind in this green box, we get against eastward Ekman transport and a positive pressure anomaly at the African coast. And coastally trapped boundary waves quickly propagate this positive pressure anomaly cyclonically around the North Atlantic basin. And this sets up an anomalous pressure gradient between the Nordic seas and in the North Atlantic Ocean. And this anomalous pressure gradient spins up the subpolar gyre. The spin up of the subpolar gyre can't be seen in this video, but you can see that if you look at a barotropic stream function. So we can now look at the response in temperature, in subsurface temperature. So at low latitudes, we see the effect of baroclinic Rossby waves that propagate temperature anomalies from the eastern boundary of the Atlantic westward. But higher north, further north, we observe a warming of the entire subpolar gyre including a larger heat transport across the Iceland-Scotland ridge. And this is explained by the spin-up of the subpolar gyre. So to summarize, wind west of Africa drives a covariation between Iceland-Scotland ridge heat transport and Irminger Sea subsurface temperature, again through a shared adjustment mechanism. So now we have seen two examples for what can drive anti-covariation or covariation between Iceland-Scotland ridge heat transport and Irminger Sea subsurface temperature, right? Wind west of Iceland and wind west of Africa. But how can we identify all such possible origins of covariation? And this is where the adjoint model comes into play. What does it mean to run an adjoint model? You can essentially think about it as running a perturbation experiment backwards. So far, I've only shown classical forward perturbation experiments. So in a forward perturbation experiment, you perturb one model input variable, for example, wind west of Iceland. And then you run your standard forward model, DRAKKAR, and then you obtain the response in all output variables, for example, temperature, bottom pressure, at all locations. The adjoint model works the other way around. You tell the model which output variable you're interested in. For example, Iceland-Scotland ridge heat transport. And you can only choose one such output variable per adjoint model run. So now you run your adjoint model, which is essentially running your model backwards. And what you obtain is the linearized sensitivity to all input variables. So wind, surface heat flux, initial conditions at all locations. And these sensitivities tell us all potential causes that could drive changes in Iceland-Scotland ridge heat transport. So I've run the adjoint model twice, once for Iceland-Scotland ridge heat transport and once for subsurface temperature in the Irminger Sea. And here we see the result. These two figures show sensitivity of heat transport across the Iceland-Scotland ridge and of Irminger Sea subsurface temperature to meridional wind stress. And we immediately notice that both of these metrics show sensitivity to wind west of Iceland and wind west of Africa, as we expect this after what we've seen in these forward perturbation experiments. And we also see that the sensitivity to wind west of Iceland is of opposite sign, and the sensitivity to wind west of Africa is of equal sign. And this is totally consistent with this anti-covariation and covariation that we observed in the forward perturbation experiments. So the nice thing about the adjoint now is that it tells us about all sensitive spots, not just the two that we tested in our forward perturbation experiments. So we can roughly identify two regions, box 1 and box 2, in which both of these metrics show sensitivity. So in box 1, sensitivity of opposite sign, in box 2, sensitivity of equal sign. And the underlying mechanisms are very similar to the ones that I've shown you in the movies. So I'll get back to this figure in just a little bit. It turns out that this figure is a main ingredient into the uncertainty quantification framework that I'll talk about next. Okay, so I'll talk about uncertainty quantification in the context of ocean state estimation. What is ocean state estimation? Ocean state estimation combines available ocean observations with an ocean general circulation model in the best possible way. So this is an overview figure from the ECHO state estimate. ECHO uses satellite observations, Argo observations, observations from marine mammals, and it combines all these observations with a second knowledge reservoir. And this second knowledge reservoir is the information that is encoded in a general circulation model, in this case, the MIT GCM. So a general circulation model knows about the equations of motion and physical conservation laws. So from a more technical perspective, here's what ocean state estimation does. We have our two knowledge reservoirs, the observations down here, and our ocean general circulation model, which generates simulated observations. And we can now define ourselves a least squares cost function, J, which measures the misfit between the simulated observations and the observations. Here's a simplified view of this cost function. Ocean state estimation now consists of finding the minimum of this cost function within the space of control variables, where the control variables are all uncertain model inputs, including initial conditions, atmospheric forcing, model parameters that are used in parameterization schemes. So this minimum now is the solution that is most consistent with both the model and the observations. To quantify uncertainty in this solution, we can look at the Hessian of the cost function, which describes the curvature. The more curved the cost function is around the minimum, the better constrained is the solution, and the smaller are the uncertainties. So the Hessian allows us to calculate how any changes in the observing system reduce uncertainty in the control variables. And we refer to this as the inverse uncertainty propagation. But most of the time, we're not so much interested in how uncertainty is reduced in our control variables, so initial conditions or wind forcing at location ABC. What we're really interested in is how uncertainty is reduced in key climate indices, such as AMOC, ocean transports, future regional sea level. And to find out how an observing system reduces uncertainty in such quantities of interest, we have to compose the inverse uncertainty propagation with the forward uncertainty propagation onto the quantity of interest. And if you do the math, you get that the relative uncertainty reduction is given by this expression here. It involves the eigenvalues and eigenvectors of the Hessian and a vector Q, which is the prior weighted and normalized sensitivity of the quantity of interest to all controls. So this expression here gives us a number between 0 and 1, where 0 means that the observing system provides no new constraints for the quantity of interest, and 1 means the observing system is optimal for the QI. So for the formulas in both steps, the inverse and the forward uncertainty propagation, we have used Bayesian inference and we approximated the posterior probability distribution by a Gaussian. And this approximation is necessary because it is computationally intractable to sample the full posterior probability distribution within this 10 to the 7 dimensional control space. And at the end of my talk, I'll talk a little bit more about the issues with Gaussian approximations. But if we accept this Gaussian approximation for now, we see that the optimality of an observing system for a quantity of interest is determined by 2 factors. The first one is marked in orange here, and it involves the eigenvalues of the Hessian. Here I'm plotting this factor lambda over lambda plus 1, and you see that the larger the eigenvalue, the closer this factor is to 1. And you can show that in the limit of noise-free observations, this factor is equal to 1. So on the next few slides, I want to focus on the second factor here. And I'll try to convince you that this factor captures the degree of shared adjustment mechanisms between an observing system and the quantity of interest. So it turns out that the sensitivity maps that we have looked at earlier can be reinterpreted in the context of uncertainty quantification. Let's say our quantity of interest is heat transport across the ice in Scotland Ridge. And we have one observed quantity by OSNAP here, subsurface temperature in the Irminger Sea. So this normalized and weighted sensitivity map here on the right is actually a Hessian eigenvector that is associated with the OSNAP observation, where I'm considering the linearized Hessian. On the other hand, this normalized and weighted sensitivity on the left is this vector Q that we've seen on the previous slide. And we've seen that the squared dot product of these two vectors gives us the uncertainty reduction in our QI by a noise-free OSNAP observation. So let's compute this dot product, or this inner product, if you will. So this is done by multiplying the sensitivities grid point wise. And there's three possibilities that can happen. The first one is that the sensitivities are of equal sign, which gives us a positive contribution. The second is that the sensitivities are of opposite sign, which gives us a negative contribution. And the third case is that, that the sensitivities don't overlap, which gives us a contribution of 0. So we've seen that the sensitivities in box 2 are of equal sign, which gives us this positive contribution here. We've also seen that the sensitivities in box 1 are of opposite sign, which gives us this large negative contribution. And the amplitude of this negative contribution is larger than that of the positive contribution, mostly because the sensitivities in box 1 are stronger than in box 2. So now summing everything up and squaring leads to an uncertainty reduction of 19%. So there are two take-home messages here. The first one is that shared adjustment mechanisms lead to large uncertainty reduction and more effective observing systems. And the second one is that destructive interference is possible, right? There was some sort of cancellation going on between the positive and the negative contribution. But this makes sense, right? This mechanism in box 1, which kind of drives some sort of anti-covariation, works against this mechanism in box 2, which drives some sort of covariation. So if we want to build effective observing systems, it is important to assess data redundancy. And we can do this within our UQ framework. Let's look at the following case study with 3 subsurface temperature observations. The first one is our usual one in the Irminger Sea. Second one is one off the Portuguese coast. And the third one is located in Denmark Strait. And it is important to note that for our UQ and data redundancy analysis, no actual measurement values of these observations are needed. This means we can test the usefulness of future observing systems before putting the instruments in the water. So these 3 sensitivity maps, they tell us about the information that is captured by these observations. And you notice that the Irminger Sea and the Denmark Strait observations show very similar sensitivity patterns, right? Both of them are sensitive to mechanisms 1 and 2 that we've seen earlier. So we expect that there is some sort of redundancy between these observations. In contrast, the Portuguese coast observation is only sensitive to the mechanism in box 2. So it might be that the Irminger Sea and the Portuguese coast observations complement each other. And this is exactly what's happening, or what we get from the formal analysis. The Hessian eigenvectors are orthonormal. So if we apply our UQ framework, this leads to an orthonormalization of these sensitivity maps. So if we orthonormalize the Denmark Strait information given the Irminger Sea information, this is what we get. Down here, you see that a lot of the sensitivity information got removed because it was redundant. On the other hand, if we combine the Irminger Sea and the Portuguese coast observations, we end up with an orthonormalized vector pair, eigenvector pair that looks pretty much the same as what we started with. So that means that these 2 observations contain a lot of complementary information. So everything that we've seen on this slide is an effect of this inverse uncertainty propagation, right? We have looked at how the observations, these three observations, reduce uncertainty in wind forcing, which is part of our control space. What we want to do next is to compose this inverse uncertainty propagation with the forward uncertainty propagation to see how these three observations reduce uncertainty in our quantity of interest, heat transport across the ice in Scotland Ridge. So the three bars on the left here, they show the effect of each observation individually. And we see that the Irminger Sea observation leads to an uncertainty reduction of 19%, as we have seen earlier. The Portuguese coast observation alone leads to only an uncertainty reduction of 1%. And the Denmark Strait observation implies the highest uncertainty reduction, 30%. So what happens if we combine these observations? Adding the Irminger Sea observation to the Denmark Strait observation does not give any extra information. And this is right, we stay at 30%. This is due to the data redundancy that we've already seen on the previous slide. Combining the Irminger Sea and the Portuguese coast observations leads to an uncertainty reduction of 25%. And this exceeds the uncertainty reductions by the individual observations. So here we see that these two observations are complementary. So let me summarize what I've talked about today. At the core of this talk was the adjoint model, which generates sensitivity maps like these. And these sensitivity maps can be interpreted in two ways. First, they systematically uncover oceanic teleconnections and shared adjustment mechanisms. And second, they are a main ingredient into an uncertainty quantification framework within which we can quantify data redundancy and complementarity. So these two interpretations taken together provide a means for dynamics-informed and quantitative observing system design. A limitation is that the adjoint only provides a linearized approximation of the ocean dynamics. So the approach that I've shown today is appropriate for capturing large-scale dynamics and Gaussian approximation of uncertainties. But very small-scale dynamics or very nonlinear dynamics won't be represented very well by a linearized model or equivalently Gaussian statistics. So how should we deal with these very nonlinear dynamics and their implied uncertainty? As an outlook, I'd just like to briefly talk about a recently funded project, which I'm excited to be a PI on. The project is called DJ for Earth, differentiable programming in Julia for Earth system modeling. And the goal of the project is to advance Julia's automatic differentiation capabilities to work for very large systems, so it can generate adjoint and backpropagation operators in Earth system models. So this enables adjoint model applications and machine learning workflows all in the same language as the underlying Earth system model. So under this umbrella, we could use hybrid approaches, right, that enhance the UQ framework that I've shown in this talk. So there are several ways to do this. We could use machine learning to speed up sampling for non-Gaussian UQ, and we could use derivative and physics-informed machine learning. Yeah, so with this, I'd like to thank you all for listening, and I'm looking forward to your questions and to discussing with you. Thank you.
Thank you very much, Nora, for this a really interesting talk and for really sticking to the allocated time. I'm sure we'll have lots of questions. You can keep your slide on the screen here. Just to the audience, as I'm not able to see all your thumbnails on my screen right now. If you'd like to ask questions, I would like you to first use the raise your hand button, but also put your name on the chat so that I don't miss any of the questions. And before we get in, I'd just like to reflect on the very last initiative you're mentioning here, as also some connections with the third keynote lecture that will happen on Wednesday, that will talk about an alternative to Julia. So the idea of using the JAX language as also a fully differentiable way to bridge a bit from machine learning and ocean modeling. So before we step in, I think there was a first question in the chat. I think Bill Dewar had a question, and then William Lovell. Bill, the floor is yours.
That was an excellent talk. Thank you so much. Very interesting. My question was, it seemed that in the sensitivity results that you were showing that there was an implicit time scale. And I was wondering if that was correct, if my intuition there was correct. And if so, what was that time scale?
Yeah, thanks for the question. So you're right. So in the sensitivity maps that I've shown, they're basically sensitivity to a time mean forcing, or equivalently, I've accumulated the sensitivity maps for sensitivity to wind forcing 1 month ahead of time to all the way 5 years ahead of time. So it was kind of a 5-year mean picture, just to keep it simple here. So what the sensitivity maps kind of merge a lot of time scales, right? Everything that happens between from 1 month to 5 years ahead of time. But so this was just to make this easier for this presentation and also the paper. But what you really want to do is, right, I've shown these comparison of sensitivity maps kind of in a time mean sense. But what you really want to do is to kind of compare them also like in time. So then you wouldn't compare just 2 sensitivity maps, but do this for different time steps too, to kind of get a handle on the time dimension too, which I've kind of dropped here in this talk. Yeah.
Okay, very good. Thank you.
Thanks for this first question. I think we have another question by William Lovell.
Yeah. Thanks, Nora, for this very interesting talk. How long do you integrate the hadron model to see the sensitivity from the African coast to the subpolar gyre? And my second question is, which hadron model do you use? Thank you.
Yeah, so as I said before, so what the sensitivity maps that I've shown, they are actually integrated for five years, but after 2 years or so, you see that sensitivity showing up, so that the teleconnection popping up from the western coast of Africa to the subpolar gyre, right? Consistent with the forward perturbation experiments, kind of takes a while to spin up the subpolar gyre and see the warming there. So about 2 years. And the second question, I'm using the adjoint of the MIT GCM here. So kind of kind of in the echo version 4 configuration. Does that answer your question?
Yes, thanks.
Next question by Mike Bell.
Thank you, Julia, and thank you, Nora, for a really nice talk, very clear and interesting. Most of the propagations you showed, or the sensitivities you focused on, were sort of propagating along the boundaries, a bit like Kelvin waves. And I'm just wondering whether, if you were looking at the influence of wind away from the boundaries, whether, I imagine that the propagation would be somewhat less, but that might be similarly informative. So I'd just like to hear what you think about that.
Sorry, you said if I looked at the influence of
say, wind forcing in mid-ocean basin?
Okay, right. So yeah, right. But it's true that the sensitivities pop up mostly at the ocean basin, because that's where we get these really strong, yeah, mostly wave-driven teleconnections. So that's the ocean boundaries are kind of the places where teleconnections are, or where signals can propagate over long distances in relatively short time. So that's why they really pop out in these sensitivity maps. And right, if we've seen in the ocean interior, there's not so much happening in terms of the wind forcing. I've kind of focused on wind sensitivity maps. What also went into this analysis is sensitivity to surface heat fluxes, for example, right? It's also part of ocean drivers. So if you look at those, then you see more, also more local patterns and ocean, in the ocean interior. So stuff that gets advected to the Iceland Scotland Ridge. Yeah, but yeah, the wind is kind of mostly propagating signals via the boundaries.
I'm just thinking that inhomogeneity might actually be one of the strengths of what you're proposing, in that you're capturing that inhomogeneity.
Yeah, that's interesting. Yeah.
Thanks for this question and answer. We now have a question by Paul Myers.
Hello, Nora. Thanks. Really interesting talk. I've got a couple of sort of questions, and I apologize if I missed it. When you were looking at your measurements, were they just like a single measurement at a single depth, or even though I'm not an observationist, but did you have like a mooring array that might have been measuring multiple variables at multiple depths, like would be happening in real observations, or did you just have a single observation at that location? And then I'm also wondering about the 1 degree aspect of the model, and whether at that scale you're missing eddies, how it represents the boundary current, and thus how that might affect the exchange of information, say even between Denmark Strait and the Erminger mooring and that.
Yeah, two very good questions. So the answer to the first question is I'm right. As you say, I have a relatively coarse resolution model, so what I'm doing is I'm computing the sensitivity to subsurface temperature over a 50-meter depth range, kind of like centered at 300 meters, but kind of in a 50-meter interval around it, right? That's all that we have in the model. And so kind of related to this is your second question. This is exactly, I think this is a big limitation of that we only have this 1 degree model, over which I'm using this 1 degree model because this is kind of what the echo state estimate uses right now. They're like now bumping up their resolution to 2, but at some point, right, the adjoint, the question is, I think if we couldn't do like a 36 degree model with an adjoint. So, right, there is only, so in general, it only makes sense, the adjoint can only capture so much, right? Kind of the linearized dynamics. And as I said here, kind of toward the end of my talk, we're missing a lot of small scale processes, eddies, and the question is, could we recover uncertainty in those with machine learning? So that's kind of what I'm interested in, kind of in future work.
Thanks. Thanks for this exchange. We now have a question by Torre Martin.
Yeah, hi Nora. Excellent talk, very well explained. Thank you. I think my question is in the same direction as Paul's. Thinking from the observational community point of view, using the adjoint model to actually design an observational network, how can we reduce the uncertainty or the risk? How can we build up trust in the model approach, really following that advice? Thinking of all the uncertainty among models and multi-model ensembles.
Yeah, I think the only way around this is to not trust a single method, right? I think at Ocean Ops 19, really the term that came up was co-design of observing systems. So we kind of, it's such an important question that we really need like different approaches, right? Different model approaches. Also there's like OSCEs is kind of a big way, or it's like a way to test the usefulness of future observing systems than this approach that I've shown today. But then we also have to talk to the observationalists. I mean, if the model tells us, yeah, you should put an observation, a mooring right here, but then, I mean, it's logistically not possible, right? It's also important. So I think, yeah, the only way is to all come together and, co-design such an observing system.
Yeah, thank you.
William, do you have another question, or is it just that you left your hand?
No, I forgot to.
Okay, good.
Sorry.
I think we do have a question by Chris Wilson now.
Thanks, Nora. It was really interesting talk on adjuncts. I hadn't seen anything like that on using machine learning to generate experiments. I think that's really novel. And I was wondering also that because, the adjunct sensitivities that you calculate, as I understand it, they're dependent on the background state. Could that be another dimension to the problem that needs to be explored? So for example, say transport through Iceland, Scotland, it might be in one 5-year period, it's got a particular sensitivity pattern, and in another period, it's got a different pattern completely. And another comment was that on how do we deal with the variety of models and maybe divergent behavior, is that a bonus about the adjoint predictions is that we can always attempt to confirm them with forward model experiments, even in the nonlinear models, high resolution.
Right, so good questions. The answer to the first question, does it depend on the background state? Yes, but the motivation here is, okay, let's say we only have linear dynamics in our model, only linear dynamics. Then actually the sensitivities do not depend on the background state at all, right? Then the sensitivity, so right, the whole approach is kind of based on the assumption that we only have a weakly nonlinear state, right? If it's totally nonlinear, the adjoint won't be able to capture this anyway. So yeah, if it's only weakly nonlinear, then we expect these patterns to be very similar if we change the background state. And yes, just the second question, we should always, or we have to verify these adjoint sensitivities via forward perturbation experiments, right? This is the only way how we can test if our linearity assumption is kind of valid in this setting. And for the mechanisms that I've shown here, right, it turned out to the adjoint did a quite good job over timescales of up to 5 years. So we saw these forward perturbation experiments, and yeah, the adjoint results matched up nicely, not just kind of qualitatively, but also quantitatively. And I've checked this, but yeah, this is always something we have to do, and this is how we can see where the adjoint breaks down. Okay,
I kind of understood the linearity assumption as not necessarily saying that there's no dependence on the background state. I thought you could still have a dependence.
Yeah, a weak dependence if you have weak nonlinearity, I'd say. Yeah.
Okay. Yeah. Thanks a lot. Cheers.
Thank you for this exchange. And before we break, I'd like to ask to give you maybe the opportunity to explain just a bit more what you raised on your last slide here. So this could you just describe a bit more in detail how you think the combination of differentiable programming, physics informed machine learning, and possibly emulation could help capture like responses involving stronger nonlinearities? Do you have like some hints to give us here?
It's something I'm still thinking about. I've actually not started working on this project yet, so I'm also curious what you think, Julien, or other people I guess also in the M2 lines project. But in general, I mean, there are several ways, right, how machine learning could help us here. So, right, we could use machine learning to, I guess, to come up with parameterization schemes, including uncertainty estimates, right? I think there are some interesting research being done in the M2 lines project right now. Or we could try to use machine learning to learn surrogate models, right, that are then that are faster to run. So this would speed up any sampling methods for non-Gaussian UQ, right? A big problem is that the posterior is, I mean, we have this huge control space, we can't sample it. So this is why I had to make the Gaussian assumption. If we have something like a surrogate model that is faster to run, it depends on fewer parameters, then that would allow us to use sampling methods more easily.
Thanks a lot for this, and I'm sure several of us would be very happy to keep this discussion going after we break. I'd like to thank you again, and I guess everybody in the room also shares my feeling that we've had a really interesting presentation this afternoon. So thanks again, Nora. And with this, you may now leave the room just before this. So we're going right now to go to the poster room that sits in the middle of the lobby. Each of the presenters of the day will have the opportunity to sit in one dedicated area where they may broadcast or share the long version of their talk with the audience. And with this, I break, and thanks again, Laura, and meet you again in the poster room in a minute. Thanks.
All right.
Thank you so much.
See you all down there.